So in this lecture we talk about fundamental group of torus and Klein bottle. So first notice that this is how torus would look like. You have two sides which you identify with each other, A, and then you have other two sides which you identify which are B and B. So this is what torus looks like, and once you do the identification you get something like this. So it's free presentation which will prove later using Van Kampen's corollary. This is it will go like this: A, B, and then we will say A, B, A inverse, B inverse is the identity map. So this will come from free product Z star Z, where this A will generate this integers and this B will generate this integers, and this A, B, A inverse, B inverse comes from going around from this vertex all the way back to this vertex. You first go A, then you go B, then this A is in the opposite direction, so you have A inverse, and this B is in the opposite direction, so you have B inverse. So this is called commutator subgroup. So this then becomes equal to, because you have a commutator subgroup like this will become equal to Z times Z. So this we will show later, but for now we are going to use covering translations to show that the fundamental group of torus is like this. So first focus on R2, and you consider a lattice in R2. So these are two copies of R2. You have a lattice in R2, and say this is point 0, 0, then this is point 1, 0, this is point 1, 1 right here, and this is point 0, 1. So everything here is an integer lattice. So this square or rectangle is same as this rectangle. So to make it more precise, you add arrows to it, and this will follow for each and every rectangle here. So you will have this here, and you will also have this here, and so on. So the first thing is that we will map any rectangle in this space to this rectangle. So to map any rectangle in this space to this rectangle, say you want to map this rectangle to this rectangle right here. Once you map this rectangle to this rectangle, in the end you just need one rectangle to make a torus. So you need to map all these squares or rectangles to this particular rectangle over this rectangle. So here this length is 1 and this length is 1. So what you do is you take xy, x mod 1, y mod 1. So this point here, once you do x mod 1 and y mod 1, this point here becomes this point right here, or say this point here becomes this point right here. Now P inverse of 0, 0 is integer times integer. So this point, if you take inverse of it, will be all these points, because this point will also get mapped here. So this complete rectangle will get mapped here. Then again this rectangle will get mapped to the first rectangle, so this point is also getting mapped here. Similarly this rectangle, if you take x mod 1, y mod 1, this rectangle gets mapped here, so inverse of this is this. Similarly this rectangle is going to get mapped here, so inverse of this is this point. So all these integer points, inverse of 0, 0 is integers times integers. Now we want to do a covering translation. Now at the end of the day you have to still preserve this yellow rectangle, because if you do not preserve it you won't get a torus. So the translation can only move the lattice from one point to another. So say you want to move this point to some point here. So you want to move this point to some point here. So to 0, 0 you add the integer mn. So say if you wanted to move it to 2, 3, so you just add 2, 3 to it, or to any particular point in here you add to xy, you add x plus m and y plus n, so as to move the entire rectangle or lattice here. So if you do that, what you have done is you essentially moved this right here, and that is m and n are integers. So you get pi 1 of t is integers times integers. So notice that this was easy in torus because everything falls into place very nicely. So all these rectangles have the arrows going nicely, so that you can place one rectangle over the other. Now if this was Klein bottle, you would have a problem, because then one arrow is reversed. So then you cannot neatly place one rectangle over another, and then you have to do slightly more work here to get a covering translation. So for torus this is easy. Now we come to RPN. So first fact we will use is SN is simply connected. We will prove this later in the future lectures. So first you have a universal cover from SN to RPN. So in this universal cover you identify the antipodal points. So for example, for S2, so this is S2, and in S2 what you do is you take antipodal points and you identify them. So there is a line going through the origin which will identify these 2 points, and that will give you RPN. So the covering translation, there can only be 2 maps, identity map and the antipodal map, because you have to preserve the projection map. Just like here you could only move it by integers, lattice points, you can only do 2 maps here, which is the ID map and the antipodal map. And this is cyclic of order 2, because you take the antipodal map and then you again apply antipodal to it, you get identity. So this is equal to z by 2z. So fundamental group of RPN is z by 2z, and fundamental group of torus is z times z. For future lectures, for some time we are going to use such a presentation of AB, A inverse, B inverse. So the z times z is same as this, AB with the commutator subgroup, which we write as this. Now this is nothing but this and this are the same. So you write this like this, because you start from this point, you go around and you come back here. So this is the same.